Hi, my name is Chris Mawata. I've been a learning tree instructor since the year 2000, and I've written more than 40 courses for Learning Tree. I also worked as a professor of mathematics at the University of Tennessee at Chattanooga and published papers in mathematics, machine learning, and visualization. I want to continue our conversation on anomaly detection, and this time let's talk about semi-supervised anomaly detection. So what is semi-supervised machine learning? As you might know, we have the concept of supervised machine learning. This is where you have labeled data that human beings have looked at, and they have decided what category it falls into. So you have a target value, the thing that you're trying to predict. In our discussion, you're trying to predict, is this data normal? Is it abnormal? So that is your target. So somebody has figured out for each of our data records that this record normal, this record normal, this record abnormal, and so on. And in supervised machine learning, we use that labeled data to train a model, which we then will use for classifying data that it has never seen. So what about semi-supervised machine learning? We shall still have a training period where we train our model, but this time the difference is that humans don't have to label the data that this is the target. It turns out that for the semi-supervised machine learning, the input values are going to be the same as the target values. So think of it as a task where you present something to your model takes it in as input, but the model is supposed to do something with it and then undo that something and reproduce the data that you gave it. So this is very similar to showing a student a picture with the intention that the student should reproduce that picture. So a skillful student will be able to reproduce the picture that you gave them. So there is training that takes place, but you don't have the need for humans to actually label the data in the first place. One place where we have semi-supervised learning happening a lot is in the creation of autoencoders. But first, let me tell you what an encoder is, and then we shall specialize it to what makes an encoder to be an autoencoder. So encoders, you have some input, let's say some English text, and what an encoder is supposed to do is to take that text and create a compressed version of it. This will be a numerical version. It will be essentially a vector, a set of numbers, and that set of numbers is supposed to encode what was in the original text. So really, what the encoder gives you, which we sometimes call intermediate code, or you might have heard of it as a latent vector, you can think of it as a set of numbers that actually contain the essence of what was said. And it is no longer in English, it is just numbers. And so one would say, well, if indeed it has the essence of what that text meant, I should be able to unravel it by using what we call a decoder. Now, both the encoder and decoder are going to be neural networks. So suppose you have an English sentence, you create the intermediate code, and then you make this claim that, yeah, that intermediate code contains the meaning of that English sentence. Well, I should be able to unravel it and have it appear in French, in Urdu, in Swahili, or whatever, assuming I can build a second neural network that will act as the decoder. So you have an English encoder and a French decoder. The totality of those two neural networks gives you a translator that will translate English into French. Now, by just hooking on a different decoder, you now get a translator from English to another language. So you are now going to have input coming in, the encoder encodes that input, you get intermediate code, now you have an appropriate decoder that goes to your target language, and out comes the output in French, in Urdu, in Chinese, or whatever. So somebody puts in an English phrase, let's just put in hello, and out comes bonjour. So what if we do it with data? This time not data that is language, but just any old data. Because remember, as far as your encoder is concerned, these are just bytes that are coming in. So if we put in data, we would expect, of course, some other data coming out of the decoder. But now let's think about it. when you built the encoder, how did you know that your encoder was working correctly? Well, the way you check that an encoder is actually doing the correct job is by putting a decoder for the same language on the other side. So if I have built an English encoder and then you hook an English decoder after the intermediate code, well, output should come English. So I should have that the meaning of the sentence that went into the encoder is the same meaning of the sentence coming out of the decoder, right? If my claim that that intermediate code has the essence of that meaning. Now let's do it to data. And when you have that coupling of an encoder and decoder such that the total work is to give you back what you put in, we call it an autoencoder. So an autoencoder is really an encoder hooked to a decoder that goes back to the same language, or in our case, to the same data. So if we do that and our data is coming into the encoder, we should have the same data coming out of the decoder. All right, so let's take a lot of normal data and let's train an encoder-decoder pair so that the data that goes into the encoder is the same as the data that comes out of the decoder. Essentially, we've built an autoencoder for our normal data. Now, think about it. What's going on inside those neural networks? They're learning the appropriate weights, both for the encoding and the decoding, so that when you put in normal data, those weights will actually undo each other in the sense that the weights in the encoder and the weights in the decoder match in that they do the job backwards and you get your data back. So if I put in data that is abnormal, well, it's going to fail because now I'm giving it data that it was not trained to encode, decode to come back to the same thing. And so one thing that you could do is to say, when I put in the data, if the same data comes out on the other side, then that data is normal. If different data comes out the other side, then I know that this is not normal. So when both the encoder and decoder have been trained properly, the output of the decoder is going to equal the input of the encoder when we have normal data, and they will not be equal when we have data that is abnormal. So in that way, we can use an autoencoder to detect anomalies. So now that we know about semi-supervised anomaly detection techniques, please join us for more content on anomaly detection from Learning Tree International.